All right. In the previous session, we looked at the I2C protocol basically, and we considered the way in which the protocol gets implemented on two lines. What is the control register format, right? We also had seen how what is the condition for starting the communication to stop the communication, right? That's called as a start condition. We looked at the stop condition of so in I2C we looked at the uh, representation of the control byte or control word, and then how the I2C is implemented using two lines, basically SDA and SCL, and a power supply to communicate between the master and the slaves, right? So that's what we have seen. I2C is a half duplex system, and basically the data frame, which includes the control byte followed by 8 bits of uh, the message followed by acknowledgement and so on. We have this kind of representation of the data frame. That's what we had considered in the previous section. Then we looked at the start condition and the stop condition. We wrote the one of the easiest possible code for start as well as the stop condition. Okay. Then if at all you want to have a repeated start, yes, we can use this code. I think that's what we had discussed so far. Right. So after this, in the next step, we want to write a code using which we try to write a byte, 1 byte of data to the EEPROM. Okay, so that's what we're going to consider first. All right, so this is to write a byte of data to, let us say, the EEPROM. Now the thing is that I need to consider what is my connection, right? How do I connect my EEPROM to, uh, say, specifically my 8051, right? How do I connect is what I want, right? So that means I have to make the connection, right, like this. So this is just an example. You can consider whatever is the question that you can try to, right, implement, right? Just change the numbers in the inside the code so that, right, we can assume the connections. This is just an example, right? Anyway, I'll draw the exact what you call the block diagram and the circuit connection we can write later by just looking at your question. Okay, what has been asked in our question paper, right? According to that, we'll make the changes. Right now we'll assume something, right? It is already known and we are directly writing. Okay, so connection is already made. Let us assume, right, which pin to be connected to which pin of our EEPROM. Let's assume as of now we know. Normally this is given in the question. So if you look at our question paper, you will see that there is a diagram given which says that, okay, this is a microcontroller and this is your EEPROM, and these are the connections. They directly mention that, okay, this is the port 2.0, port 2.1. They are connected to pin number whatever pin number in your EEPROM it's given. Okay, I just have to say in my code that, okay, right, if I say P2.0, it is SDA. If it is P2.1, it is SCL. I just have to initialize that in my code. Okay, so anyway, that will do when we write a the complete code later. Okay, so we'll write a complete code, I told, right? So when we do that, we'll do this. Okay, so now right now it is a part of the code which is, I can call a function called write byte to my EEPROM so that it writes 1 byte of the data. This is what is my intention now. So how do you start writing? Before you start writing, you should initialize, correct? So initialize in the sense I have to start. First I need to say that, okay, the master will uh, insert or assert the start bit on the I2C bus, correct? So this has to be done. Now when I write a code, I have to do this. This is something like the flow chart, all right, or the step-by-step procedure which I want to follow, right? So first, what you are going to do, you make the master, right, inserts the start, right? You can call it as a start bit, okay, or the starting condition on I2C, right? And after the start bit, what you are going to do, you will pass the control byte, okay? So then you pass on the control byte, right? Because the specific EEPROM will have certain address, right? You have to make sure that, yes, you are sending that address, indicating that I am master, I am talking to a particular slave, right? Only that slave should respond me back. Okay, so pass on the control byte to the EEPROM, then you say write bit because you want to write. Okay, followed by a write bit. So if you look at the right position in our control register, what is that write? For read it is 1, for write it has to be 0, correct? So in the sense, make the write bit as 0. Read write bit, you r slash w bar bit, make it as 0, right? Write bit. That implies wherever you have r slash w bar equal to 0, make that, right? Once you do that, you wait for the acknowledgement. I need to wait for the acknowledgement. Once you see, now if the master does not receive the acknowledgement from the EEPROM, it keeps on sending the control byte, right? So let's write that. If no ACK, this implies, right, repeat sending the control byte. Okay, until you receive the acknowledgement. All right, but if the master receives the acknowledgement, right, then it sends the address of the cell where it has to store the byte, because in the inside the EEPROM, let us assume we are using a EEPROM which has 16 locations, right? A not to, basically A not to A15. Okay, so you will, the master will send the address of that location where it wants to store the data. In EEPROM, I have 16 location, A not to A15. Where do you want to store? Because you need to pass an address, right? Okay, so upon receiving the acknowledgement, what you are going to do, right? Send the address. Send the address of the location in the EEPROM where the data needs to be saved or stored. Okay, then, right, the data will follow immediately after that, because you say the, you will send where you want to send the address. Okay, then you will pass on, uh, first you send the address, right, immediately followed by you send the data, right? So then you say stop. Okay, then send byte to be stored. All right, followed by stop the communication, stop condition. So fundamentally, this is how you write 1 byte of the data. Okay, all right, so let us go for a code. This is again a function, right? It's going to be used as a user defined function in our main code. Okay, so anyway, we will not write all these user defined function once again in our main code because it already exists. Okay, right. So this is the code to do that. So you don't have to return anything. So the function is write a byte to EEPROM. This is the user defined function. So you see what are the various parameters I need to pass. I need to pass, right, uh, the address, correct? Address is integer, right? You can call, uh, again, there are many ways to represent that. If you are sending only unsigned integers as an address, you can declare it as unsigned int. Okay, so anyway, it's fine, you can use unsigned int. So but I prefer, just since our intention is just to understand the code, right, and how to write a code, so I don't want to go that level of coding. Okay, I'll just write int address. Okay, so that is the address I'm going to pass. This address is inside the EEPROM where I want to store. Then you see you have a byte. So byte, the data which you store there is a character type. Okay, because the 0x, so maybe you write a data like CD, right, which is a hex data. So I have to include that in the character format only, not in the any other format. Is it okay? So that's why I declare the next data as a character. So character, and the name of that data is byte, which I want to store. Okay, it's of size 8 bits. Okay, this is what is the program's first line, the function. So just we are following this step, right? All these steps. So I know that I have to initialize. How do you initialize? That is called as a start function. So let me just see what was the name I gave yesterday. I'll use the same thing so that, okay, start I2C. That's all. Okay. That's all. So you know that what's going to happen, right? The start bit will be inserted over there. Now you see, right? There is what is called as a device address. Okay, so where is the device address in our, actually I'm looking at the this one, right? I'm actually looking at the control register, and we are referring, we are trying to make a reference to that, right? So I'm understanding that. So this whole thing, so starting from the control till here, okay, so till here, this part, right? When this, I'm looking at the next one. Okay, if this is right, acknowledgement is not one, right? What I'm supposed to do, I have to keep sending this control byte again and again, correct, until you get this. So how to access that? That can be accessed by using a specific command, right? That is called as the slave address, right? You can use it as a slave address, or some will call it as a device address as well. Okay, so now you see this is a condition while, right, the again I'm going to write another function later. Okay, that is called as the write I2C. I'll write this immediately after I write this function. This is another function. Okay, while the write I2C of inside the write I2C, I'll be passing a variable called device address. Device address, its next position indicated by +0. Okay, that is 1. Whenever this is the condition, what I'm going to do, I will keep sending the start. Okay, start I2C, keep repeating this, right? Whenever the condition is satisfied, you will repeat this. Okay, now, okay, this is done means if at all the condition is not satisfied, you will come out of this loop, and now you start, right? Actually, it means acknowledgement has been received, right? And you don't have to send the start I2C once again. Okay, when that is a condition, what you do, you write your address. Okay, so now you see this is the fundamental idea that recall the 8051 architecture. 8051 has 8 bits of data buffer. right? Data buffer means it is the one, either you keep the data ready which you want to send. That's the first thing. Okay, whenever you want to send something, you will put that 8 bits over here. That's the first thing. Other option is that the same data buffer can be used whenever you receive something from some external interface, some external device. The device sends the data CD. The CD comes and sit here initially. You can find the data received in the data buffer. Then you put it into whichever register you want, register A, register B, etc. Okay, so there is a data register. So the idea is here is that whatever address I am supposed to send, because you see in our steps, the next wait for acknowledgement is over. I got my acknowledgement. Next is, if no acknowledgement, keep repeating. That's also done. Fine. Now my next step is, upon receiving the acknowledgement, right, send the address of the location of that EEPROM. Correct? So I have a data to write. What is your data? Just look at this. So the data I want to send is byte. Okay. Where you want to store? I want to store at this address. Where is this address? It is inside the EEPROM. Now I need to send this address, right? So this address is supported up to 8 bits. Okay. Address supported is up to 8 bits. So that means I need to bring all the 8 bits into the data buffer, because this is what I want to send to EEPROM, right? So whatever you want to send to the EEPROM, it should be present in your, it should be present where? It should be present in the data. So there is a direct method which can make sure that, right, both the things can be done simultaneously, like this. So anyway, I'm going to write a function, this function later. Okay, so that is write I2C of, you know that you have an address, correct? Address shift by 8 units. Okay, so that's what the 8 address locations will be directly sent to your so address will be shifted by this much amount. Okay, so you see that address will be passed on to the EEPROM. Okay, that is passed. Now what I want to send, see, address is sent. When the address sent, what do you want to send next? Send the data, correct? So that is, once again, write I2C. What is the data? Data is is stored in the form of a byte. Okay, that the name is byte, correct? Over here, this one. So I send address, followed by I send the data. Once the data is sent, what is the next step? Stop. Let me just check the name of the function we wrote earlier. It's already there. Yeah, it's a stop I2C, correct? On the right side. So this function will be executed, right? That is stop I2C. So close this. So this whole function is responsible for, right, writing 1 byte of data. That's all. Next, you want to write another byte, call this function again. Put in the address, put the byte which you want to send, call it again. That's all. Okay, so this is how it's going to be done. Is it okay? Fine. Now, uh, let's write another code. Okay, so that code is to read, right? Next is to do this. Read byte of data from the EEPROM. So just recall what should be the procedure, right? Initially, master is the one who is responsible for initializing. So master decides that I want to read a data. So master inserts the start bit on the I2C bus. Okay, and immediately after the start, send the control byte to the EEPROM and make the R by R/W bar equal to 1, because this time you don't want to write, you want to read. Is it okay? So let's write that. So master asserts the start condition on the I2C bus. First step, right? Then immediately after the start, right, it will send the control byte to the EEPROM with what is the change? R slash W bar should be equal to 1. That is the reading condition. Now I want to read. Previously it was W bar, so it was 0. Correct? Okay. Then you will wait for acknowledgement. Okay, you keep waiting for the acknowledgement, and if the acknowledgement is not received, continuously send the control byte. Okay, so if no no acknowledgement, this should imply continuously send the control byte, right? Repeatedly you keep sending. Okay, now let us assume that you received the acknowledgement. Once the acknowledgement is received, what do you want to do? Now you want to read, right? You want to read something. So whenever I say I am a master, I want to read a data from a slave, which is the EEPROM, right? Inside the EEPROM, I know that I have 16 locations, right? So I should say from which location, exact location I want to read, correct? Once the acknowledgement is received, right, you have to send the address. You have to send the address of the location inside the EEPROM, inside the EEPROM, right? Where okay, from which it has to read the data. After sending the address of the particular location, right? Now you will see that you will send a repeated start condition, because once again it has to start. Okay, so remember the difference, right? In case of writing, this issue is not there. Only when you read you have to do this. Okay, so insert the repeated start condition on the I2C bus. Okay, again repeated condition we already have written, right? We are simply calling that. Now what happens, right? Once you put the repeated start condition on the bus, now read immediately after this, you read the data. Okay, now the data come when you put the repeated start, the machine, the slave understands, that's the EEPROM understands that, okay, now I have to send the data, right? Put the slave puts the data on the I2C bus, so simply read it. Okay, so read the byte of data that appears or appearing on the I2C bus. Simply you have to read it. Okay, so then, right, you can simply stop it, right? The communication is over, right? Stop condition. Okay, right. So this is what is the procedure to be followed to read a data, that is uh, by specifying the address on the EEPROM and reading the data that comes from the EEPROM on the data line. Okay, so let's try to write a simple code to implement this. Right, now you see, do you have to return something or it's a void function? What do you expect? My function is, say, I'll write this. So uh, read, say, byte from the EEPROM. Okay, this is my function. So what you are supposed to pass, you will pass int address. So from this address, read me the data. Okay. So my question is, what will come here? Is it a void or you are supposed to return something? If you recall, I write void when I don't return anything, something like this, right? So I pass my address, I pass my data, so it will be returned digits. Okay, it will be returned to that location, right? But now you see, I what is the intention of this code? You are reading a data, correct? Return, you need to return the data, correct? So data is in the character format, so you will write a character. So you are going to return a character now. Character read byte, this is my function. Are you okay with that now? Okay, so it's, that's why it's a character. Okay, fine. So now initialize that character. So okay, so this is character. I'll write rx data, received data, I'll initialize with the 0. Okay, absolutely fine with that, right? So I can initialize with what I want. I start with this. So what is the first step the master performs is, right, start I2C. It will insert the start condition onto that, correct? Next, you wait for the uh, acknowledgement, right? So what is that? I have to say, I'll, this is my condition. While the write I2C, this program we have not written, we'll write it later. Okay, of device address. Okay, device address plus 0 equals to 1. When this is the condition, right, you keep repeating. So that is start I2C should be repeated, right? Once this is done, you pass on the address, correct? So that is write I2C of the address, 8-bit address, so you have to move it by 8 positions. So okay, so that's the condition. 8 positions you shift right, and whatever is your last byte will be sent to the sent through the wire. So let's assume we have simply 4 bits, say 1010. This is the one which goes out. Okay, then I need to shift right, so this becomes 101. This is shift by 1 unit. This 1 goes out, then the next what happens, 10 comes, this goes out, then 1 comes out, then lastly this 1 also goes out. So 4 times if you want to move the data, you have to move it to right by 4 units. Okay, but right now I'm moving it by 8 units because the data, right, whatever we want to pass is of size 8 bits. I hope it is clear. Okay, right, so that is done. Now you see, let's go back to the steps, right? Once the acknowledgement is received, send the address location on the EEPROM, then a repeated start condition is the next case, right? So I'll just go back to check what was the name given to the repeated uh, function. Yeah, this is the one. The repeated start I2C is the name of the function to do the repeated start. So according to the steps only we are following. So this is a repeated start of the I2C. Okay, I'll call this function. So repeated start will be done. All right. Now right, I need to say that simply you receive the data, isn't it? Just check the next step. Insert the repeated start condition on the bus. Read the byte that comes from, right, your machine, right, from your slave. So it's, I'll put that is Rx data, received data is equal to, I need to write another function that is read I2C. Okay, write I2C is one function which we are supposed to write. We will also write the read. Okay, right. Now, once that is done, right, you can stop. Stop I2C, right? So now I2C, the protocol stopped, but my data is present in the Rx data, which I need to return. So return Rx data. So, and you close the function. That's all. Is it okay? All right. Now, so let's look at the functions. We had to write a function, right? That is a write I2C and read I2C. Both functions will write here. Okay, which actually includes the acknowledgement that is coming from the slave as well. I need to include. Okay, right. Now you see, when I say write I2C, the write I2C will send a, it's a bit by bit process. You are trying to send a bit. All right. So this is the function which we already have used. So you remember, it's a bit. The return value will be a bit. Okay. Write I2C. You see that write I2C will always, right, you are going to send the character byte. Okay. Oh, we missed one step, sorry, because I'm calling it as a character here, but I never use the character here. You see, this byte, whatever I'm seeing here, right, or this address, what I'm seeing here. Okay, so this address is not character, right? So there is a mistake. So it throws up an error because it is integer. Correct. So what I do, I have to make a type conversion. That's what we missed. All right, so I'll just make that correction over here. Right, so you understood, right, what exactly is happening, right? I declared that as a int, but I'm in my function, in my write I2C function, whatever I'm sending here, right, I'm declaring that as a character. You see here, see here, it's write I2C. I have to pass a character to that function. I cannot pass integer. So that's a problem, right? But anyway, I cannot keep this integer, because on the contrary, we have the characters also being sent. So let's keep the biggest one here, that is a character. Okay, so we'll try to, I'll make a type change here. Okay, I'll try to make a change, even if that same problem exists in the read as well as the write function. Okay, so what I do, I will, let me erase this. Okay, slightly I'll push these two lines below. We'll just move this. Okay, we'll make a type conversion here itself. I don't actually have to do this. Right, I2C address, address is moved. Okay, let's try to do it in this way. So write I2C, right, uh, typecasting can be done using the parenthesis like this, right? So this is, uh, you have to tell what is the output you want, output data type, that is character. Okay, character of my address. Okay, so now the address gets converted into character and will be written onto the I2C. Okay, so wherever we use the write I2C, I should make sure that I am writing right here also. It's the same thing. Okay, here I'll add a sentence that is write I2C of the character type. I'm changing the character because address is in integer. I get converted into character of the address. Okay, so that's the change you want. Next, you see we are not using the write I2C again anyway. Okay, so this is the important step. Is it okay? Okay, now we'll come to the actual function which is used to write the I2C. Write a data and it returns saying that yes, writing is done or not, because you see after you send a data there is a acknowledgement bit coming from the slave, right? So that is what I am returning here, right? Whether it is successful or not, I will come to know after this. Correct. Okay, so let's start with, so I define a character, right? I denote that as I, right? So how many characters you can send? 8, because my intention is to send a byte. So we'll start with a for loop. For uh, I is equal to 0, I less than 8, I plus plus, right? During this, when the I changes from 0 to 8, so make sure that your first the clock becomes 0. Okay, so SCL is equal to 0, right? That's a condition. SCL will be low high. When SCL becomes high, right, within that from low to high transition you do something. So make SCL low and call a delay, right? That is I2C delay. It's a value. Okay, I2C delay will be a delay value. You can call it as 10, 20, 50, whatever, right? That count will be calculated by the machine and it will do nothing during that period. Now, so I will check that whether the received byte, okay, is something like is lesser than I, and this should be ANDed with 80. Okay, 80 in the sense, okay, this is a condition for reading. So I'll write if, what is that? The byte, right? I can see that byte here, right? That byte which is passed to the function, you can see that we have passed the byte over there. If the character byte, so that byte I'm considering here is lesser than I, that's a condition. And okay, you are going to perform the AND operation. So okay, AND operation with the 0x80. So what is 80? It is 10000000, right? I am going to perform the AND operation with this. Okay, so only when you have the last bit is done, right? Because 10000 means you have only the last bit, right? Only MSB is 1, correct? Only under that condition, right? It means sorry, if byte is this and this, if that is a condition, what you do, right? That data will be sent on the bus, so that is SDA is equal to 1. Okay, else what we do, we make sure that SDA, the data is 0, you're not sending a data over there. All right, once this is done, you send the data, one bit will pass, right? As soon as a bit will pass, right, I can see that I have to call a delay. Okay, so delay of again the same number, I2C delay. Whatever is the delay amount you want, you do this. Immediately after this, make the SCL, the clock high, call the delay. Okay, I2C delay. So this is inside our for loop. This repeats 8 times. for all the 8 bits of data. Okay, now what you do, you will wait for this data has been sent. You want to wait for the acknowledgement, right, from the slave. So why it is necessary? Because you see, I send this data, correct? I have to wait for acknowledgement. Until you receive acknowledgement, you cannot go for your next 8 bits. That's the condition. Okay, so that's why I'm waiting for the acknowledgement. So acknowledgement bit to what I receive, I'm going to put that, sorry, where is the function? Yeah, I'm going to return that here, okay, as a bit. That's what I'm returning. I have to return something, so I have to wait. Okay, so let's do that. So what happens after this 8 bits of data transmitted, right? You make SCL equal to 0. You make SDA is equal to 0, because whatever comes on that line, I need to pick up. Okay, right. Now, call delay, wait for some time, delay of whatever I2C delay you want, right? Then make SCL equal to 1. When SCL equal to 1, the slave comes to know that yes, the master is ready to receive the acknowledgement. If there is a acknowledgement, master will be ready. Okay, SCL becomes 1 means it will understand. Okay, so as soon as SCL becomes equal to 1, the acknowledgement bit will be placed on the data line by the slave. Okay, so what you need to do, you just have to return whatever comes on the SDA. That's all. Correct? SDA may become 1, acknowledgement is received. SDA is 0, acknowledgement is not there. That's all. Right? That has to be done after the clock becomes equal to 1. That's all. So this whole process is the write I2C function. Whenever the one single bit, one byte I want to send, I'm doing this procedure. Is it okay? Similarly, I had used another function, right? If you see, that is the read I2C here, okay, in the previous function. So I have to write what is that read I2C doing. Okay, so let's write that. Okay, let's directly write the function as required. So now you see, read I2C is also going to return, right, the data which has been received, correct? So this also has to return something now. So I'm writing this way. So this is a character type, character read I2C, and right, this read I2C, if you remember, if you see here, the usage of read I2C, somewhere I did, yeah. So read I2C, I'm not passing anything inside into the function, okay, but it returns something. That's all, right? So the received data is of Rx data. If you see, it is a character, correct? So I'll just go back to the top to show you. Yes, so character Rx data is a character, so it has to return character, but you don't have to pass any variable to the function, correct? So return type is character. Read I2C of, you don't pass, it's void. Are you okay why we are doing this? Yes. All right. So let's define the required variables. They are of type characters. Okay, I, D, and I'll put Rx data as well. Okay, equal to 0. So again, normally we read 8 characters at a time, 8 bits at a time. So for loop, I equal to 0, I less than 8, I plus plus. Right. The reading procedure is this: make SCL equal to 0, then make SDA equal to 1, call the delay of whatever number, I call that number as I2C delay. All right, I call this I2C delay, then make SCL as 1. Is it okay? When you make SDA equal to 1, Immediately after that, whatever appears on the SDA bus is your data. Okay, right. So what I do, I'll do like this. So make D is equal to SDA. Whatever is on SDA, you read it. But I have to convert the RX data, which is of 8 bits. Only when I have 8 bits, I can do something. Okay. So RX data, you see initialized with 0, right? On the top, you can see RX data has been initialized as 0. So if you want to add something to that, right? This 0 means it has 8 zeros, okay? All 8 zeros. Now, whatever comes first, I'll put here. Then whatever comes next, I can put here and so on, right? So what I do, I'm going to perform an OR operation, right? OR with the 0 is the actual value itself, right? Whenever you OR with 0 with the 0, it's 0. When you OR 1 with 0, it is 1. So whatever comes in that is present in D, I can simply do that. Correct? Bit by bit, I'll do this. So this is Rx data. Initially, this is 0. Perform OR with D, right? Move it to left by 7 minus ith position. Correct? This is 7 minus I because, right now first data goes here. Remaining is 7. 7 minus 2 is this position, right? Or from the left you calculate. Correct? Actually, that's what is happening. That's why I'm doing shift D, right, to 7 minus ith position. That's what I'm saying. You see, if you remember earlier, we wrote something like D, move it to right by 8 units. Now I don't move right. Now I move to left because that's the incoming data right now. Okay, so that's the reason, right? So now you see at the end, once this loop is over, but I'll finish the loop here. 8 times you read the data and the data will be present in the Rx data. Okay, D is a single bit. I am converting a single bit into 8-bit data here. Is it okay? Because whatever I want to return is a 8-bit data. That's all, right? So I have to do that. So Rx data is equal to Rx data ORed with the D shifted to left by 7 minus I units. Every time I changes, you see that you shift it to the left by 1 unit lesser than the total size. Initially I 0, so it will go to the 7th position, then 6th position, then 5th, then 4th, then 5. Like that, I fill all the 8 bits. Right? So start 7 minus I0 is 7th position, 6th position, 5, 4, 3, 2, 1, and the 0th position, 7 minus 7. So that is the 0. You see, you fill up your 8 bits. It's clear, right? Okay, right. So I fill up and I give a small amount of delay before it does the next thing. So delay of I2C delay. Right? So now you see your data is present in the Rx data. So return that. Return Rx data. And close this. So that is the read I2C. Is it okay? Right. Now we have to write one more function. That is which one? Did we write the delay? No, we called the delay so many times, but we never wrote a function to delay, right? I have to define that as well. So this is the next function. So you see, it's simply calling delay, so you don't have to repeat anything. So that is void delay. All right, you pass integer, right? I called maybe just now you can see here. I called delay of I2C delay. This is an integer value you are passing, right? Give a delay of this much, right? So int d. Okay. So what I do, I call int I. I'm not doing anything. So simply for I is equal to 0, I less than or equal to d, I plus plus, do nothing, give a semicolon. For loop will run so many times. That's all. Okay, it's a delay, do nothing. All right. So simply for loop will run so many times. That's all. Is it okay? That is a delay function. You can write anything inside here if you want, right? Definitely that should have nothing to do with the actual code. That's all. Simply spend some time here. That's all. Okay. So anyway, I wanted to generate a small delay. That's why I'm simply running this code so many times. Okay. All right. Now let us try to write the main function which does the job. Right. See, this is how it is. So for which we will refer to say your question paper. All right. So let's quickly look at the question paper, and they have given a circuit or something. I remember. Yeah. So let's go to that question. Question is something like this. You have 8051 over here, right? You have the DS connected over here. Yes, that's the EEPROM, correct? Now the P 0.0 is being used as the clock, right? And they already mentioned that P 0.1 is the SDA. This is what we want. Okay, all others are the power supply. You can see that there will be a crystal connected to X1, X2, ground. The VSAT connected to the sorry, VBAT is the battery, right? Where you connect a 3 volts battery. So it has nothing to do with the programming. So you don't have to worry about that. All other parts are already right. You have to make a proper circuit. Yes, yes, yes. So everything else is done. So when I try to write my code, this is how the code looks like. Okay, so this is the main function to implement this. So all the user defined function which needs to be implemented, we already have written. We simply have to use them so that you implement the code, right? So the job has to be done. Whether you want to read, whether you want to write, you have to do that. Okay, that's all. Right. So we'll start like this. So this is the I don't have to return anything. Void main, right? And again, you can write a void inside this brackets as well, because you don't have to pass anything. So void main void is also valid. No issues, right? Even if you don't write, doesn't matter, right? First, I want to say, right, whatever I want to receive. All right. So that's what the character Rx data or Rx byte, because Rx data already been used. But anyway, that's a local variable. Nothing happens even if you use the same thing. Okay. So, but anyway, just to avoid the confusion, I'll just change this as the received data, or Rx byte. Received byte, initialize it as 0. And I want to show how to send. Okay. So send byte is A. I want to send A to the machine. Okay, now you see, right? The SDA, you have to tell where is it. Okay, what is SDA according to you? It is P 0.1. Okay, SCL is P 0.0, right? Okay, so P 0.0. In a sense, whenever we try to use this, the machine has to access these two pins. Are you okay? Right. Then let's move further. I just have to uh, directly call the write, because I have the data readily available with me, correct? Right. So simply call the function the write. Or okay, I'll tell you one more thing, because sometimes people expect you to initialize uh, initialize the whole setup, right? Maybe they expect a initialization as well. Okay, so initialization happens very simply in this fashion. Okay, that is like this. So you can say that the SDA, pass SDA as 1, pass SCL also as 1. So both make 1 1. It means it is initialization. That's, I'll just write here. This part is the initialization. Okay, there is a difference between initialization and the starting of the process. Okay, so right now we have not done the start function, we are simply initializing. But you see, where is the start? Start is already there inside our function, right? So if I go for the read byte of EEPROM, you see inside that I have a start I2C, correct? Also, if I go for the write operation, write byte EEPROM, that also has the start I2C. So you don't have to call this start I2C separately. Simply call what you want. So let me assume I want to, first I want to send a data. Okay. So how do you send the data? Call the function, that is write byte to EEPROM. Right? This was our function. We already have written that. What you are supposed to pass? You are supposed to pass a address, maybe 01 is the location where you want to write, and the data is already written, that is a send byte. Simply call this. It executes that part of the code which we have written and writes the character A to the memory location 01 in the EEPROM. Right? It does that. Now what you want to do, you read, because my next operation I want to perform is a read operation. So read operation will put the data into Rx byte. Correct? So Rx byte should be equal to, call the other function, that is read byte EEPROM. Read this. You have to pass the address 01. Right? So that data comes here. You receive the Rx data, right? Then I don't have to return anything, so you don't have to write a return. Simply close this. This is the driver function or the main function which does your job. Okay, so read and the write completely done. Okay, now you see in the question they already mentioned that the read I2C, start and the stop are available. They are assuming that they are available. The other part you need to write. That's all. Okay. So this is how you interface an EEPROM to the 8051 uh, and perform the communication in terms of reading and writing of the data between 8051 and the EEPROM.